Chapter 5, first two sections on deformation of axial loaded members. The learning objectives for this section are to be able to calculate the deflections of material subjected to axial loading. And the material can have varying cross sections, varying material properties, or varying loads. We'll see that show up as we do what I love, the wedding cake problem. The equations that we get from the study guide, really there's the one equation, and we use it a couple different ways, but it's delta is equal to PL over AE. Delta being the deflection is equal to P, the load, times L, the length of the member, E, the material property, Young's modulus, and A, the area. Let's dig in. That is what we need to know. Delta is equal to PL over AE. And I will, I write it PL over AE, even though I think the book I just did EA. The reason I do it this way is because it forms the acronym. It's all about play. I love to play. It helps me remember it. So PL over AE is what you'll see me write all the time. But this equation shouldn't be, I don't want this equation to just sit there. I don't want to just throw this out and go, hey, that's what it is. Let's start out with some definitions. Let's start out with Young's modulus is equal to the stress over the strain, and the stress is equal to the force over the area, and the strain is equal to the deflection divided by the length. Those are all basic equations that we've had. If I want to go back through, this is chapter 4, this is chapter 2, this is chapter 3. That's how everything tied together. And so now I look at this and I'm going to say, okay, delta, I'll start out over here, and I'm going to write delta is equal to epsilon times L. Epsilon is equal to sigma times E. So epsilon is equal to sigma divided by E. Sorry, I knew something was going wrong. Sigma divided by E times L. And now sigma is equal to force over area. My E is still on the bottom, and I got an L out front. Well, let's just rewrite that. FL over AE. Well, fine. Let's call that P now, because it's the force, it's the load, and that's where this equation comes from. We often get equations like this, 5 variables. We're not going to derive that. No, some of these are really simple, and you will find throughout machine design, throughout your civil engineering stuff, you're going to find these equations that we get. We can go back and do some simple algebra and come up with the equation that we're required to know at the time. So here's this equation. Now, that is one way of looking at it. Delta is equal to PL over AE. And that's going to say if I have a box and I push on it from the top, and let's say that it's rigidly mounted here on the bottom, I put a force P on that, and now you want me to tell you how much that squishes. That's great. All I need to know is this length, that area, and the material properties. And I can do that. And we will run a number of problems where we do that, but that's not really that interesting. So we have to work hard to make this interesting. And so what we do is we get the wedding cake problem. The wedding cake problem looks like this. Now, It's called a wedding cake problem because the way I drew it, it looks like a wedding cake, but the reality is it's got three different materials. So I liken that. I would like to liken that. This is like a cheesecake. This is a cheese layer, and I say that because that's the biggest. And then I'm gonna say this red layer is vanilla, and the green layer is my chocolate. And each oh my chocolate. I can't even spell chocolate today. Got an A in there. Chocolate. Okay. That has a particular Young's modulus equal to, and vanilla has a Young's modulus, and the cheesecake has a particular Young's modulus, and they have three different areas. So there's an area for that, and there's an area for this. Oh, I tried to get red. There's an area for that, and there's an area for that. And so you wind up doing, how much does the top deflect? What's the deflection there? Well, it's actually the deflection of the chocolate. The deflection total is equal to the deflection of the chocolate plus the deflection of the vanilla, right? Yeah, vanilla plus the deflection of the cheese. Cheesecake, though, not cheese, not straight cheese. And so we've just changed our problem so that now we go, okay, now we have to do all three. And for this problem, the load is the same through all of those. So you could do it, but oh, you know what? Maybe there's a different length for each of them too. So then you might get that the deflection total is equal to P times, and then we have to start hitting an L over AE because that's unique for the vanilla, and it's unique for the chocolate, and it's unique for the cheese. And that's our next level of problem. And each, so this is just the deflection of one section, and then. It can get more interesting. We can have a problem where area is now a function of x, that the bottom of this is fixed, and we put a load on the top, and now we're trying to find out delta. But if I would write the equation now, it's PL over A as a function of x times E. And really what we need to do is integrate all the little deltas, right? And so we can put, this is really my delta, well, that's my delta total. It would be, instead of an x, it would be the integral delta is equal to the integral from 0 to L of P over A as a function of x, Young's modulus, dx. Actually, not a del x, it's going to be a dx. But I can do that. Or I could have my force as a function of x, but this could be some, we don't want that. This is possible, but those are very interesting, and really it's just a large sum. We could do that as, which is what we did with the coffee cake problem. We did a sum with 3 elements. This is just a sum with infinite elements. That's axial loading, and we're going to go play this out over a number of different scenarios. Now, this lecture is only about section 5.1 and 5.2. I want to talk briefly about 5.3 and 5.4. What we get there is systems of members. And those are not very interesting to me. One, what we're going to do is we're going to say, hey, I've got this and this, and this point is mounted rigidly, and that point is mounted rigidly, and then I'm going to get a bar that goes up like this, and I'm going to get a bar that goes like this. And when I put a load there, F, then how does this position move? Well, this has a compressive load. This has, I'm going to draw a compressive load, and this has a tensile load as I'm trying to stretch it. And so, yes, this point moves, but honestly, it moves a very, very, very small amount, probably smaller than the manufacturing tolerance when I put that load on it. So I'm not very interested. Further, there's a lot of math that goes into this. When I can use the tool that we're playing with on the side, the FEA, I can use the FEA to solve that. Now, I also want to tell you something about FEA. FEA assumes that things don't move. FEA makes this assumption, the very small deflections, because if these deflected a lot, then I might have to change my force vector, and I might have to. So we already in FEA are making this assumption that things don't move a lot. I don't think there's a reason then to go back and say, hey, we're going to say they're not going to move a lot just to do a lot more work. If things move a lot, they break. And so these problems in section 5.3 and 5.4 are not very interesting to me, so I'm skipping. Next presentation you're going to get is example 5.1. I didn't throw the sketch in here, but I believe it's a wedding cake problem. I'm not saying it's cheesecake, vanilla, and chocolate. It's probably aluminum, brass, and steel. It doesn't matter. We can do the analysis no matter what the confectionery challenges we face. I hope you're doing well. I'll talk to you soon. See ya.